that better?
Uh, Marginally. It's difficult to hear you.
Okay, how was that? No?
Yeah, I can hear you, but I've got a head piece right now. So
Okay, I am on a system here that on a Cisco system. Is that
oh,
better
there
for
we go.
everyone?
That's much
Yeah,
better.
yeah.
Okay, much better. Okay, awesome. Maybe I'll just begin. Move over here. So the agenda I have today is I'll showcase kind of two projects and some lessons learned for that, and how that really gave us the seed and the mandate to create what's called a technology and innovation lab here in Enbridge. We now have two, but really those are the two projects that gave us the mandate to do so. Today we have about 12 production systems doing all sorts of optimization, simulation workloads, AR, MR related advanced visualization, and obviously ML and AI workloads. And that spans across our business units with a particular focus on liquids, and there's a reason for that. But as you may not know, Enbridge is an energy transport company. It's the largest in North America, and it runs the most complex liquids, gas, and utilities in the world. We transport close to 28% of U.S. crude. We have about 30,000 kilometers worth of liquids pipeline, about close to 40,000 worth of gas pipelines. We have about 14 wind turbines, solar. We just getting into the offshore business, and I'll talk a little bit more about that today. So the first project I want to talk about is a pipeline integrity project. It's a really interesting one that was done up maybe a couple of years ago, but the results are still relevant about 2 years ago, and we're taking that system and we're scaling that out. So in this particular problem, the problem that we're trying to solve here is there are sloped movements in a given area, and it requires a combination of multiple complex and disparate data sets, including initial measurement units, LiDAR, inclinometer, and strain gauge information, and more. In total, there's about 136 data sets that need to be not only ingested, transformed, just munged together, and it's a whole variety of fidelity within that data set. So different sources of systems, sources of truth that need to really be time aligned, cleansed, imputed, and now an algorithm kind of developed to really help understand, the coincidence of defects that we find in terms of crack corrosion and dent, to actually make a recommendation whether that piece of pipe, is subject to a leak, and that's obviously something we wish to avoid. So we created a solution just as a POC, but now we've taken that solution and we're going to make a product out of that, and that's part of the technology innovation lab that's been created here in Enbridge. So that solution is pretty cool. It allows very clear visualization of 136 data sets all in one location. In conjunction, we are allowing our subject matter experts to interrogate that data. Now, there's a lot of lessons learned. We are very much using immersion technologies to do so, and we've ran into some limitations and some lessons learned. I want to be transparent about that. So really, the experience is to be to have a network-like experience on this prototype, which now becomes a product, to allow teams from different regions and different subject matter levels. So you may be a pipeline expert, a material science expert, an integrity expert, to look at that same set of data at the same time and interact with that in unison. So that's a very important component here. So it really has increased our accuracy for assessment for high risk areas to be undertaken with a very high degree of confidence. So this gives the ability for easy communication of the current state of the pipe to teams either inside or outside the company. So everything that we do around the pipe obviously has regulatory, legal ramifications. We keep all that information. It's called records retention. Everything's in our lake, so we have a way to archive that and label that. The data flows are, I'll show you the architecture behind that. The data flows are quite straightforward, but there's a lot of them, obviously. So we can view historical data, and we can actually overlay predictive future behaviors, and then document, and also have auditability. Whoever touches that data, we're able to kind of lock that down and see who looked at it. Jimmy looked at it. Okay, what decision did he make? And try to bring a lot more rigor into that whole process. So at the end of the day, we're trying to. We have several challenges. So I'll just kind of summarize that. Currently, the way to do this is not very quick. It's very hydraulic, and we need to have an effective visualization technique and a decision support tool through ML AI to scan all the geo-hazard sites that we have. We have a lot, 30,000 kilometers worth of pipe. Today, a lot of the information is kept within kind of traditional technologies like Excel sheets, and probably you guys can resonate with that. A lot of spread marks out there. The team struggles to look at all that data sets, especially LiDAR, ILI, IMU, strain gauges, and other types of data in a very system enterprise level approach. So, for example, it's really hard for our SMEs to hunt for that one cell in a spreadsheet to make a determination versus another cell. So we want to really up the game and perspective on that data. So that's very important. And the key decisions being made from the intersection of the data allows us to reduce that blind spot. So we can actually better predict with expert judgment to support that what is the hazard trend brewing and occurring, right? So I'll stop there before I get into the value proposition. Was there any questions around that? There's a little bit of video of a very small section of the video of what is working. So again, the value proposition, I can't really go into the numbers, but really to improve the geohazard assessment process, speed, understanding, and collaboration through enhanced visualization with obviously a huge machine learning and AI component, and also enhanced communication with external stakeholders and regulators on this. So let me just move forward. So as we delve deep into this a little bit more, you see that on the left-hand side there is a terrain being projected here. There are multi-resolution satellite visualizations of the selected land envelope, which is the LiDAR, and we blend that with what we know to be the 6 pipes that we have that we're inspecting. Now we're running a pipeline inspection gadget. It's called PIGS. It's advanced technologies with kind of 6 sensors within a given device that runs through our pipes and records everything from vibration, temperature, a whole bunch of information. We blend that as well. The issue we're finding is 2 years ago, our vendors that provide this technology for us, their files that they're using to produce that is kind of hundreds of megabytes per run. Using the latest technology because of the resolution, the size is 4 terabytes per run. So we found ourselves this year with a problem. How do we ingest all that information seamlessly at the scales that we need it across all of our lines? Very, very difficult to do. And that's the product that we're building today, is to find and develop a scalable, robust system that's able to ingest all that data and start kind of munging through that data, transform it, and then feed our machine learning AI algorithms. The stuff that we're adding more is the voice control, the filtering aspect, the terrain exaggeration. So you can actually time dial all the different segments within a given pipe and view the inclinometer information, which is a measurement of the slope changes, the caliper data over a given time period as it was recorded, and then start correlating that information. Now, the great thing about it is the visualization's there, and we did the bashing, the clustering together of all that information. That's really the approach that we took with a little bit of modification. And then on top of that is we had subject matter experts to validate that position. So we entered into kind of a heat map where they can interrogate the data. The interaction could be a lot better because what we're finding is they want to kind of parse all that information based on their perspective, and we're trying to inlay that capability into that product that we're trying to build. Now, the pipeline inspection, as you see it there, we can call up and we can time slice all of the different segments of the pipe from left to right and slide that intersection, and then focus a couple people on that particular area. The great thing that we found by doing this initially is we really focused our subject matter experts who have like a PhD in material science or failure rates and all that stuff, and avoid that time that they would normally spend for getting the data, right? So in a given sample 8-hour day, typically they would use 6 hours just to grab the data, munge it, clean it. Well, we've taken that off the table with the data ingestion pipelines that we do have. Now they can focus basically 6 hours out of their 8-hour day on the results of the data itself, which is a huge win, Now, the inclinometer information is visualized in the train model in a 2 visualization modes, dependent and data processing. So we actually can see how certain data sets, as it overlays itself, is giving benefit or not. So we're starting to create an inclined behavior model that can be viewed at a linear depth and showing movement direction. We're kind of building that in. That's part of the plan that we have for this product. And so what that really translates to is a lattice mesh model that will mimic Earth movement across the terrain. So behind that is like a simulation model that we're speccing out as to feed that kind of mesh movement. So we're looking at cross industries to see if there's anything that has been developed, and there has, in particular the gaming industry, that we can bring to bear to this one. So I've spoken a lot. I'll maybe take a pause so perhaps you can maybe ask some questions on that. Anyone?
Tony, with such large data sets, I guess accessing the data in real time is almost like that's, I guess, or just accessing the data in general. Is most of that stuff occurring on-prem, or is it? It would have to be
all of our stuff is off-prem. It's in Azure.
Mm-hmm.
That's our vendor right now.
Nice.
And it's in our lake. So we've added a lot of extensions. We're trying to look at the TSI time series insights, see if it can help us out there. But our technology stack is Databricks, and we feed that up into a Cosmos DB, and you'll see that a portion of the architecture that I'll present. We're starting to move over to Cosmos DB because it gives us infinite scale without the performance hit that we would normally expect in a traditional kind of hosting side, provisioning of the data itself.
Mm-hmm.
And we're now looking at the semantic layers of it. So depending on the role you take, Jesse,
mm-hmm.
so you may not need all that data to be surfaced up through that visualization, right? So we're being very careful of how much we serve, who needs it, and how they want to present it to them, right?
Interesting.
Yeah. So it's a large problem. The thing about Enbridge is because of our size and complexity, we cannot find an off-the-shelf solution for a lot of things that we do. Trust me, we look. And what we're finding is, and that's why we built this technology innovation lab, is we're pursuing these product builds because the size and complexity is so large that we have to build it ourselves. So, and that's really the commitment that we have from our board to invest in Enbridge with employees and all that stuff to do this stuff. Yeah. Okay. There's just some testimonials here. So here's just a couple of diagrams here. It doesn't get. This is very logical. I couldn't get approval to get the physical diagrams or architecture, but we have a whole kind of content acquiring data from third party. ILI is inline inspections tools, LiDAR. Formatting was huge and still is a huge issue. Format schema changes that they make. We're still trying to contend with that and put some more, intelligence on the front end to kind of adapt to schema changes on the fly. You would think that they would standardize the stuff, but no. Across different vendors, we have different sensor technologies coming in, and we're trying to standardize. We're still trying to standardize the input format. Ingestion is pretty much the same. We're using Data Factory to do that, via version 2, if anybody knows that. And we've structured the contents into a data lake storage, which is kind of in the middle. So that follows the taxonomy, which is asset-based. So we've done a redo within our file structures within our ADLS 2, Gen 2 we're trying to move to, where it's a little bit more agnostic to the business units and departments. So one thing that happened last year is we got an organizational change, and before, it's a lesson learned, we had our data lake structured based on BU. So we found ourselves kind of, okay, now what do we do? Because that department went away, no longer exists. So we had to redo our data lake taxonomy and nomenclature to be a little more genericized, such that it's now asset focused. So a pump is a pump is a pump, and then we put metadata around it to define where that resides and how that data comes in. There's an IoT component to this, which I won't talk about, but that involves streaming real-time data into our lake to augment and time align with I guess what you call the cold data, if you will, coming in. So we have a fast hot streaming coming in, and batch data, which is the ILI, LiDAR, formatting of all that stuff coming in as well. So we do follow a Lambda architecture. Many of you probably know that online here. And we're trying to keep, according to Hoyle, the playbook. We've made some extensions and recommendations back to Microsoft to influence their product development within Power BI, time series insights, and a whole bunch of other components to accommodate for the scale that we need. And they've been quite responsive. Now, the data management visualization side is kind of an interesting one. I didn't split it out, but in there's a provisioning side, transformation, provisioning, and semantic layer that we can talk about if you wish, but I didn't really emphasize here. So once again, we're using Databricks Delta to do our transformations on Spark, and we are referencing some kind of custom Python code, which represents our machine learning, or mainly our clustering algorithm, but we are taking an ensemble method and technique to this as well. And then on the right-hand side, HoloLens application. The newest product we're building, we're emphasizing more of the UWP, Universal Windows Platform. So for those who probably know UWP, it gives us a huge flexibility in repurposing that application, which is currently on HoloLens, to work on a Windows 10 application, iPad through AR Kit, into Xbox, which we haven't tried, and into our Microsoft hubs, which we do have several in the company. So the Microsoft hub is like a Microsoft Surface on steroids. We have a 55-inch unit across Toronto, Houston, Edmonton, and Calgary, and we're building that application for interaction. We also have like I said, Windows 10 application as well that hosts the same logic that renders the visualization on the front face for different stakeholders. So if you're a bit like a back-end subject matter expert, wearing a HoloLens, cool, but it's gonna wear on you quite quickly. So we're trying to cater to different usability requirements, which is another kind of area of learning for us as well. Right? Not one solution will fit everyone. It doesn't suit everyone because of effectiveness and suitability requirements, which are different depending on your role. And also, if you're in the field, you can't use certain form factors as well. So this began as a ML and AI project, but it soon became very much a logistics issue, a user-centric issue. Quite frankly, our predictive model was the easy part. It was truly we didn't spend too much time on it. We kind of figured out what technique to use and how to validate it. It's all the other bits and pieces that need to come together from a systems perspective that really meant a lot. Now, just move on to there. So again, this we call it the AR/MR application, but what drives it is a simulation model and also an ML and AI model. But our prototype is 6 lines in our right-of-way for Cheecham terminal, and we're going to move this over as our base model, our base approach platform for all our kind of slope issues that we're finding. and also integrity approach as well as our main workbench, if you will.
So Jesse here, the value case is really incident prevention, but I guess ultimately you could use this to defer maintenance and plan your maintenance as well.
Yeah, absolutely. There's derivative kind of benefits to this. So, integrity has a budget. What we're trying to do is reduce the unnecessary digs that integrity recommends, because there's a risk profile that we have. We want to maintain below that risk profile, and kind of before any perceivable risk we go after, right? But there's a lot of type 1, type 2 errors in that approach. So we're trying to use the technology, disruptive technology, apply it in such a way that we can maintain or actually reduce the risk profile, but not incur any more type 1, type 2 kind of errors that we do see in the traditional technique. We're still learning on this, but really that's the ultimate goal, right? So it's very much taking, for example, a time-based maintenance approach, traditional, versus a condition-based maintenance approach.
Which would save a lot of money. You'd think.
Money isn't the focus, but
Sure.
Definitely we want to redirect our resources to spend time. If we have 8 hours in a day, we truly want them to spend time on the areas of true risk, not on the ones that are false positives, if you will. Yeah. Now I do have a slide or a video that I'm going to kind of show you. I don't know how it comes across. Maybe I'll have to, let me stop sharing. Maybe I can just share that video. I've never tried that one before. So share a window. Media. Can you guys see that?
There we go. Yeah.
I'm going to play this. I really don't know how this is going to work. So we're zooming out. This is Cheecham Slope. We can rotate it. On the right-hand panel, you can actually inspect the terrain, look at the topographical map, the LiDAR results, the inclinometer, all the information coming in on one segment of terrain. And then we can time dial this. We can view the pipe and slide this across. And all those heat maps that you're seeing is 136 data sets coming together, moving kind of in unison. I don't know if this is coming through the video at all, but no?
Yeah, we can see it, Tom. Yeah.
Okay. So that's really what that project was all about. Just back in here. So what to know? There's a whole bunch of lessons learned, which took us a long time to kind of go through, but it gave us the impetus to, once again, create the lab that we now have. There's 2 labs that we have, and then now move towards building a platform for integrity, and also this platform can service for leak detection and a whole bunch of other departments, not just for liquids. The great thing about this is we backpacked this solution around and really gotten huge interest and support from our gas and utilities area. So having one product service many different units is where we're heading towards. Now, yeah. So before I move on to the second project, first time attending one of these things, and I'm not quite sure that hit the right level. For the propeller heads on the call, probably not. We can probably get into a little bit deeper discussion on the approach. The actual algorithm, what was the considerations there, how do we choose it? But I decided to keep at a certain level, and maybe another meeting we can dive a little bit deeper on that one.
Any questions so far? Okay, let's proceed. Yeah,
Okay.
very interesting stuff, though.
Okay, so the second part is the green power. So here's the kind of the background. I don't know if you guys know Enbridge, but we have a lot of wind turbines, about 14 onshore, where we got a whole bunch of offshore in the Rampion region. That's our commitment to move towards the offshore. Just to kind of level set kind of the knowledge, wind turbines, back in the Persians, they use it to kind of mill and crush grains, and kind of the design paradigm hasn't really changed up until now. It's really all about a conservation of energy, and I'll talk a little bit more about that, dynamic range, adaptable wind structures. But back in the 1919, around there, a person named Albert really coined the whole kind of the wind turbine blade, and he investigated kind of the maximum efficiencies allowable, and it's called the Betz limit. Does anybody online have a background in wind turbines and whatnot, or know of them or how they function? No? Okay. Well, I'll keep on proceeding there. So there's a whole bunch of things that in the 2000s, back in 500 AD and even 1999, that we can take advantage of dynamic range, adaptable wind structures. So the newest modern kind of wind turbines, they actually anticipate wind profile, attack angles, and they adjust the pitch and sometimes the yaw of the system to make maximum the power output. So dynamic range, adaptable wind structures, material science and services, forecasting wind patterns and curtailment situations, and more efficient motors. That has really still helped. But even today, we're seeing about 40%, 42%. Now, other vendors may claim higher, but that's what we're seeing on a daily over average over the year. 59.3 is that kind of envelope that we're seeing that could theoretically be achieved, but that really hasn't changed. And over that time, kind of the wind structures and the airfoils, and that's what it really is. And this is somewhere way back when, I can't remember where I pulled this from. Hasn't really changed at all. And again, this is conservation of energy formula. I'm not going to get into what we actually went through to validate.
Oh, Tony, we don't see the screen right now.
Oh shoot.
Yeah, no problem. Yeah, we switched, I think, to the video, and then it.
Let me do this. Show. Okay. Apologies. Thanks
no problem.
for me back up then.
Great, thank you.
Yeah. So hopefully you guys are seeing this.
Mm-hmm.
Yeah, that was my first couple of minutes about way back when, all the way to the 2000s. I can kind of give you numbers on megawatts that we're producing back onto the grid. And this is a comment I made about the Betz's limit, kind of describing that. How over time, it's because of taking advantage of dynamic range, adaptable wind structures, material sciences, and even now they're forecasting of wind patterns in a localized area, very difficult to do, and turbulent airflow and how that kind of affects it. At the end of the day, just to replay that, it's Bernoulli equation that we're kind of dealing with here is the conservation of energy, how that wing airfoil, I'll bypass that, how that airfoil translates kind of wind energy into mechanical energy into an electrical energy. On the very bottom there is a representative of a 40-meter blade that we have in our wind turbine. It's just some nomenclature. Where it's attached is the root. On the very top part is the tip. Leading edge is how it's attacking a given wind profile, and the trailing edge, that's where kind of the wind kind of falls off there. Today, what we have, I should probably zoom this thing in, is 40-meter blades. 40-meter blades. I don't know if you guys have perspective on that, but we are moving to 80-meter blades. So the best reference I can provide is in an Airbus A380. The wingspan on that is 80 meters. So one blade is the wingspan of 80 meters, and these are offshore assets. So primarily our assets are 461 wind turbines, about close to 1,400 blades. Today using 40-meter blades, but we're moving towards 80. Now the physics, these megastructures are completely different. So that's something to contend with. We do have a solution that's working for 40, but I'm not confident it's going to genericize to 80. So again, blades rely on airfoil designs from aerospace. And the problem we're trying to solve here, I should have stated that at the beginning, is to really estimate the remaining useful life, to move from a time-based maintenance to condition-based maintenance approach here. And it's not as simple as identifying a machine learning algorithm and applying it. There's a whole bunch of systems analysis that needs to be done. Obviously, because the blade is in earth oil and they produce lift, rotation, that we're all accustomed to seeing. Just wanted to say that obviously is our revenue generator. Without that, and with that going down, we stop generating revenue. So it's very important for us to maintain that structure and hopefully predict the remaining useful life or time to failure. So I don't know what else I wanted to make mention of this.
Hey, so sorry, it's Jeff Russell. Just a quick couple questions, only because it's somewhat topical. So I've been looking at putting a windmill at my residence. So there's microgeneration, but using a vertical axis windmill rather than the propeller type. I don't know if you can speak to that at all, or if it's of any relevance.
So, my background is not a wind turbine expert.
Okay.
So I'll state that up front. But part of what I did with two other folks that provided a solution was to learn as much as we can about this. My background is electrical engineering formally, so I unfortunately I cannot comment on that. But I did learn a lot about the physics and science of this stuff. But again, I cannot comment on that. I only can comment on the stuff that I looked at. But maybe after the call, I wouldn't mind conversing with you on that.
For sure, that'd be great. Appreciate it.
Yeah. So maybe to give you some perspective, we do actually, I said 14, but we have 19 wind farms and growing, 461 turbines, 1383 blades, and the new ones, the offshore ones, we're getting into a region, Rampion, English Channel, southern UK. I think there's about 114 wind turbines there, and each of them are about 3.4 megawatts each. They output 400 megawatts in total. So there's the ratios and the forces on these wings are immense. So the gearbox planetary system inside the housing there, they have a ratio of anywhere from 1 to 90 and 1 to 120 around there. If you look on YouTube to find, I can't stream it because it doesn't look good, but if on YouTube you can look for wind turbine failure or a blade failure. There's one that happened in Europe that's just quite dramatic. If you see it, actually see it spinning out of control, and you see the whole 40-meter blade just break right off. Now, it was for a different reason. It was because the brake control went away, but it just kind of goes to show you that we want to get ahead of it, because the repair and downtime and secondary damages being seen is quite substantial. Now, here's a display of one of our wind turbines. It's in Ottawa region, and that's the nameplate, what it actually kind of outputs. And here's just a photo shot of one of those assets. And approaching this problem it isn't just getting the data, munging through it, finding correlations, making sure multicollinearity isn't there, blah blah blah. No, it's not that. It's not just that. You have to actually go out, in my view, touch the asset, go out there, see what the physicality is, have learnings from it, and then that'll help you develop your machine learning and AI approach without a question. And we did derive a lot of insights just by going out there and kind of figuring things out, looking at those defects being recorded and identifying that this is the wrong defect, or it doesn't contain enough information, or more of the case, the data quality is very poor or inconsistent or incomplete or incorrect. So the effort going down through here really involved the whole experience, climbing 200 feet, free climb. This ladder you're always attached, but this is held on by magnets, kind of ferromagnets on the side. They don't drill it into the side of the tower there, but these are very powerful. If you stretch your arms across with these two magnets, if you bring your arm close within 5 feet, they slammed together. I believe a person who was installing it lost a finger by accident. So it's really an interesting process of them kind of installing these things. So went up on the turbine, that's me on the right. Now you know how I look. But kind of looked at all the different aspects, went into the wind turbine itself, the 40-meter blade. These point marks are actually where defects were located. They're a laminated type of configuration, and they're kind of wood constructed. These were, at the time, tanks being constructed, but now they have different types of kind of designs for wind blades. These are just a few cracks that we saw, and kind of superficial kind of unraveling, unwinding of the polyurethane coating inside, the peeling off. But it's just to correlate the defects that we're seeing in the data, how it's being described, how it can be repeatedly reproduced in the kind of capturing and even in the visualization, and how it translates into reality. So what we did was we took SCADA information, the defects that I talked about prior, the weather information, a whole bunch of things, and we pulled it into an approach which really talked about estimating, predicting the time to failure, remaining useful life, and we focused on kind of the risk associated with that. The funny thing is before we got onto this project, there was over 400 defects being defined, classification of defects. And after we did a site visit, and this was over about a year, we started bucketing, we started bucketing these defects into a more genericized approach, and we went down to 40 classifications from 400. At the end of the day, it was a very interesting kind of outcome. We were able to kind of validate the predictions with a high degree of accuracy, over 90%, and we're actually using it for wind turbines. We're actually putting, I think, IP around the specifics around this solution. Let's see here. The next one is this one. So the data set and features that we actually did use was, the set that you had in there. So back here, we combined it with SCADA, defects, weather, and the defect portion are this set. So the defect type, the component, the subtype, the reference, the location, the chord position, the radial location, distance from, the length, and there's a few more other kind of data sets that we combined. One of the techniques we used was a random forest tree, and then that wasn't the only one though, but that's just giving you an example. And then we started classifying based on the risk tolerance, and we produced some really good outcomes from there. Now, to get to this state, once again, it's not just physically visiting the site. We had to go through this stuff, causal loop diagram, understanding the physicalities. So in this, I don't know if you can zoom in. So we did an analysis where the door, I don't know if you can see this at all, guys. It's fine. So they never did the analysis. It's cross-sectional lateral view. We had to hand create all these diagrams again. We had an Ishikawa diagram. We met with our subject matter experts on the field to figure out what caused a failure of these blades. We documented it, and we spent over a year getting the data to validate this intuition, understanding the causal loop diagram to know that that's another path of figuring out what key features would be indicative, strongly correlated with a wind turbine blade failure. And then we mapped all this stuff. It's in a system. I'm just giving you snapshots on areas of concern. So if it's the base footing, the dorsal cross-sectional view, where does all the defects reside, and why is that? So it may be kind of a leading indicator of something, or a lagging indicator of something. Maybe a manufacturer's defect, a design flaw, maybe how we're operating the wind turbines. Maybe we're over-operating in a certain time period. If there's a wind profile that's higher than the suggested manufacturer would ask us to operate, then we would take note of that in the system and really make some operational recommendations. At the end of the day, the impact of the solution really translates into a higher degree in confidence of predicting blade failure, but also enabled our team in the field. So when they took a snapshot of the blade and the defect, and they hand wrote that report, it took 3 months, on average 3.5 months, to move from the field identification of defect into the back office for a subject matter expert to review and to make a decision and a judgment to say, yep, we have to reinspect, we have to repair, or we have to replace. 3 months. So in that time period, 3 months, the defects, as you can imagine, can propagate. The defects can get worse. It can combine with other compound defects to make the situation that much more critical. So we were able to reduce that from 3 months down to 3 days. And then we have intention to reduce that down to 3 days, down to 3 hours. And we have the plan as a product path to add visual analytics and have a kind of a UAV kind of go out and inspect these blades themselves with some embedded analytics in them. So a lot of different kind of options that we have there. So I'll move forward here. So again, our data flow solutions component is very similar to the one in pipeline integrity. The thing that we have is we do have a reference architecture that we're using for the last 2.5 years, 3 years, and we're mandating that everyone's kind of using that approach. So this one's a little more detailed treatment in that regard. The only thing I would say that's changed is we're progressively addressing technical debt. ADF is just one version, so we're moving from V1 and V2. That they're actually not V1 and V2; they're completely different. Same with the Gen 1, Gen 2 for the data lake. That's something that we found out it's not quite the same. It's not an easy lift, but we're addressing that. So from moving left to right, data sources, ingestion, transformation, provisioning, and then publication of that content for consumption. In this case, the Power BI application. So our Power BI application is O365 bound, and we can access that anywhere. And we update all the content there on a daily basis within a 3-day window. The subject matter experts are able to look at the defects, get a prediction from our algorithms, and then validate that position. So we are always reinforcing the outputs. Let me move past this one. This one's just the number of kind of turbines we have and the amount of inspections that we are planning at a certain time period. And really the outcomes are that predicted defect based on inspection data and actually more, time to failure, remaining useful life, and that kind of classic bathtub model. We're able to kind of focus our people, reduce the kind of the capital budget, operational budget, to do maintenance planning. And I think that's it. Now I just wanted to kind of make a plug for the Technology Innovation Lab. So I've moved from my role as being accountable for the data science practice here at Enbridge for the past almost 3 years to take up a position for Technology Innovation Lab. So our mandate is to build products within Enbridge, and this is our kind of process. So we started the Canadian lab in February. We launched that in February 6th, and we launched the US lab on April 23rd. So our mandate is now a lot larger. We can apply disruptive technology to solve some key Enbridge problems. So again, the complexity and scale that we're seeing our problems is we just can't buy it off the shelf. And we have 14,000 people, very highly specialized, trained individuals doing their job. So we've identified 12 products we're building within the Technology Innovation Lab. We launched on 2 of them, and we're bringing another 2 into the lab. So when we solve these problems, our intent, our mandate is to disrupt the energy industry. So we are going to solve these problems using the 12 products. We solve for Enbridge. Presumably we will have solved it for the energy industry as well. So the products span all the way from predictive maintenance of large assets reciprocating rotating equipment, to optimization of our power, to predictions of kind of market conditions, sentiment analysis, to the stuff that we're doing right here, which is integrity, leak detection. So a lot of individuals and folks are kind of coming together for that. Now, the Innovation Lab, this is our kind of process product lifecycle from ideation pre-discovery all the way through minimum viable product build, which is in the middle, to scalability, sustain, and retire. We're tying ourselves into our larger TIS organization. So the LIV is the TIL is a combination of both IT and the business coming together, which has support from the C-suite. So they're all supportive and funding this whole approach. And the roles that the composition is a whole bunch of kind of roles that Enbridge is not accustomed to. These are skill sets that in our traditional sense we don't typically have. But today I think we've had 1,600 applicants, which is great. We had about 100 interviews, and we're still hiring kind of people for the lab. So I think that's all I've had. I don't know how many people are on the call here. I have to look at my Skype again. But were there any questions anybody had?
Yes, I actually have 2 questions. Can you hear me?
I can.
Yes, the first question is, as the wind turbine design trends change, how feasible is it for you to keep redesigning the workflows and retraining your systems to adapt to the changes?
So there's that's a great question. There's 2 answers to that. So we have Vestas. That's our main wind turbine. But as we acquire wind turbines and even our existing mix, and that players like Siemens and all that stuff, their design of their wind turbines are different. So their defects are going to be different as well. So what we're finding is we're trying to first classify the defects in a generic way across that, independent of kind of the wind turbine manufacturer. So
yes.
Some of them don't have a key piece of design feature that another wind turbine does, and as a consequence, they have defects around that. So that's we're still going through that analysis to see how we can genericize some of the defects that we are seeing across different manufacturers. That's number 1. Number 2, tuning of the model is always ongoing. So we always have a mechanism internally that we built in to not auto-tune, we're almost close to auto-tune our models to understand if within an envelope of predictability, we can use rock curves and all these other kind of techniques, classic, but we are always with a subject matter expert to provide judgment on whether our model is drifting. All models drift, so it's a matter of detecting when that model drifts, the conditions for, and then refactoring it and retraining that. That's something at scale, very hard to do, but we do have a technique that we're trying out, and we've seen some good positive results, but it's not automated fully. It's very, very difficult to do. In addition, we're playing with a different CI/CD approach, not for this project, but the CI/CD pipeline is actually, it will help us with that, answering that question. So we're playing around with blue-green deployments, canary deployments, darkened deployments, just to get ahead of trying out different models in a very limited fashion and getting the results in as fast as we can.
Thank you. And then the second question was based on, through your trend analysis and the data you've gathered over the years, for example, have you ever had to send back some of your observations upstream to the manufacturer so that the designs can be tweaked to eradicate those problems?
So this is the great thing that we originally had difficulties with. So manufacturers, they manufacture obviously the wind turbines, and we're having the same problems with our pumps manufacturers. They don't necessarily want to share their defect information, their warranty information, and low-level design information. So that's a trade secret. I can understand that. That's an intellectual property. It's really hard for them to share that with us and with probably any other consumer. They see that as maybe a business opportunity for them. That's always been a problem. So the ideal situation is to kind of identify lessons learned, feed that back up to the manufacturer to improve their design, and we have yet to kind of do that last step. It's the agreements are kind of, it now comes down to commercials, and depends on how you structure commercials. And these blades aren't new. These are more older wind farms. So we're maintaining, we're operating them. So in terms of them, they don't make these blades anymore. That's my point, right? So these progress past this.
Thank you.
Sorry, so Jeff Russell, another question for you. So do you track efficiency based on like wind speed and direction as to which blades or which generators are the most efficient?
So for this set of blades, it's very limited because of the vintage of these wind turbines. What we can do, we don't have pitch yaw control, really, auto rotation of those things. But in the newer turbines, it's all performance management. So that's why we have a link back into SCADA, this one, which is supervisor control. I think everyone knows what that is. So ultimately what we want to do is have a feedback loop in there to actually now optimize. This started as a kind of a blade remaining useful life, but the future definitely should involve real-time feedback loops of operational conditions and weather information, the whole of sorted content to make kind of localized adaptation to always maintain that performance profile, that performance envelope. But right now, it's really based on the capability of your equipment, whether you can do it or not.
Okay.
Sorry, this is Leslie again. I asked the previous two questions. A question about predictive analysis. Do your systems tie into meteorological data to predict what weather patterns will be? And also, how do your systems compare predictions versus actual? If that storm eventually comes and is worse, or if that storm ends up not coming?
So as a matter of course, what happens is that the weather information does come in, and it gives locally the operator's indication of whether they should curtail, shut down the wind turbines and whatnot. So right now they have a person in the middle to affect operations. How it dovetails into remain useful life, it's more from a historical perspective of what actually happened. So we can actually make some correlations whether that defect was a result of that lightning strike or not, right? So that's where the correspondence happens, but we're trying to move towards more of that operational real-time kind of and leading indicator of, hey, a large storm cell's coming in, what can you do? Operate your wind turbine using this operational profile as opposed to your normal one. So we want to get into that. This is with the amount of wind turbines and the variation, heterogeneity of the equipment that we do have, we're finding that it's very difficult to find that genericized approach, but we're trying to kind of analyze that right now.
Thank you.
Any other questions?
Hi, my name's Aaron. I was wondering if you could talk a little bit about what your training data looks like and what kinds of predictions you expect to get out of that from a machine learning approach.
From the wind turbine one?
I'm thinking the wind turbine example, yeah. What kinds of specific inputs, what kind of resolution, how far apart? I mean, you're looking at historical weather, you're looking at current weather, and then how does it give you information about what you should be expecting in the future?
Well, see, so the defects that are being captured as reports now is a system that you can actually go online to make those notes. They actually, one of the defects is, and in the field when they look at it, they may comment that, oh, it looks like it's a lightning strike, okay? And there's some using through the image capture that they have, the subject matter expert would make that determination to say, yeah, that it was a lightning strike, that we did have an event like a week ago, and it was on top of kind of the localized wind farm. So, and then we could have another secondary inspection. So a lot of, if you look at the workflow, it's really hard to explain, but the workflow, there's a lot of times when people physically inspect it, go up to the tower, re-inspect it, and then to conclude that it was a lightning strike. So what we're trying to do is kind of cut all those steps out and really infer that that was a lightning strike, and then they can actually, confirm that is the case. So just to remove all those kind of key steps. So we're using alignment of when that occurred, what that looks like, I guess secondary effects of that defect, and we combine that. One of which is using a decision tree to look at that. The other one is the other techniques that I talked about to see where that occurred, and so forth and so on, and then make a determination of prediction. And that ultimately, that prediction is reinforced, if you will, by the subject matter expert. And there are times when we do disagree, which is a great situation. Now here's an opportunity to ask why, and that has been fed back into the model as well. So we basically adjust the weights, if you will.
Gotcha.
That's great. Well, we're out of time here, so thanks so much, Tony, for your presentation. Extremely informative and interesting to see how you guys are attacking this stuff. And I know there's tons of lessons learned here. I've got a lot of notes, so thank you.
Okay. If you want to send out my coordinates, my email contact to folks online, I'd be more than happy to connect with people.
Wonderful.
Thanks.
Okay. Thank you, guys.
Thanks, Tony.